Here we are. As I was saying earlier, we did our model. Now we're trying to solve it, finding the eigenvalues of this. So we're at the MATLAB part here. So let's go over to MATLAB. Let's clear all old variables. Clear all. Let's define, well, we don't need to define the coefficient matrix. And so the coefficient matrix is right here. And it was, if you remember, -3/10, 1/18, 1/5 for the first row, 3/10 for the second row, -2/9, and 1/10. And the last one is going to be 0, 1/6, and -3/10. So I'm not going to output it because I don't want to clutter this. Let me just check. -3/10, 1/18, 1/5, 3/10, -2/9, 1/10, 0, 1/6, and -3/10. Then what I'm going to do is I'm going to find the eigenvalues and vectors. First, I want to check if the eigenvalues are real or imaginary or repeated. So we have a 0, 0 eigenvalue, and then we have these two. So I'm going to go with a different technique because I don't like the Jordan. I don't trust the Jordan all the time. So if the eigenvalue is 0, 0, then I'm going to find the individual eigenvectors. And that's going to be done this way. So I'm going to say that this is the eigenvalue, and I'm going to save it into this because this is a vector, it's a 3×1 vector. And so finding the individual eigenvalues, I'm going to take this matrix A and I'm just going to rewrite it like this. And I'm going to subtract the first eigenvalue, which is going to be eigen 1 from the first entry here on the second row. I'm going to subtract eigen 1, and then here on the last one I'm going to subtract eigen 1. And let's just output it to see what it does. So I think it subtracted 0, 0. Basically it didn't subtract anything. And now I want to say that I want to solve for the eigenvector k. So I want to multiply it by, well, let's augment it. So we're just going to keep it like this, and we're going to add a 0 at the end of each row, and 0 here. Now what we're going to do is we're going to put it in reduced row echelon form. And if we put it in reduced row echelon form here, we should get the eigenvalue, well, the eigenvector. So we press Control Enter, and we get this. So now we get that the third row is linearly dependent on the other two, which is what we are expecting. So now this is the same thing as saying 1 times the first entry, we'll call it K1, minus, we don't have K2, K3 is minus K3, and all of that is equal to 0. And then we have K2 minus 1.8 K3 equals 0. So now what do we do? Well, we can add this to both sides, and it comes over here with a positive right here. And now we know that we can say that K1, we can add this to both sides. And so now we just need to define K3. So K3 is going to be what? K3 is going to be, well, how do I express 1 over 8 as a fraction? Well, let's see. 18 over 10, that's the same thing as 9 over 5. So if I want to make this an even a whole number, I need to multiply it by 5. So let's say that K3 is 5. So if K3 is 5, this is going to be 9, and this is going to be 5. And here I can check 1.8 times 5, and I get that the answer is indeed 9. So assuming that I did this correctly, this would be our first vector. So I'm going to define the first eigenvector with a lambda equals 0. And that's going to be K sub 1. I'm going to define it as 5, 5, 9, 5. Okay. Now we're going to do the same thing for the other two values. Well, actually for the other two values, it's slightly different because we're going to want to put it with the cosines and the sines. So let's see if the Jordan actually works, because that would make it a whole lot faster. So if the Jordan works, Jordan of A, and we're going to say that that outputs the vectors and the values. And let's comment this stuff out real quick. And let's control enter. First, we can validate this one right here. So vectors. So we had one vector that was 1, 1.8, and 1, which is the same thing, because if we multiply by 5, we actually get this vector right here. But now something interesting is that from this, we can pick out the imaginary part and the real part. And so it happens to be this way. So forming the solutions. So one solution is going to be simply the eigenvector. So that's going to be vectors, and the first one is real. So that's going to be vectors 1 multiplied by the exponent of the eigenvalue, which is, well, we don't even have to put it, but I can put it in here, which is just 1 right here. Or I could use values here, because we can just use the Jordan. So values, and what is the exponent here? Well, this is 1, 1, 1 comma 1, and then it is times t. So we need to define a symbol, and we define t right here. And this is our first solution. Our second solution is going to be exponent to this real part of the eigenvalues. So I can say, this real part. So I can say values of 2 comma 2, and then I just want the real part, which I think in MATLAB was like this. I don't fully remember, so let me put it in here. Help real, not found. So I think I'm gonna have to dig a little bit into one of these to remember the command, because the other thing would just be to hard code it. It's not good coding practice, So see, I used to do it with the RREF. Let's see if there's a, if I find that command. Let's see. So here, here is all RREF. So here, maybe not here yet. So yeah, I'm just gonna write it in there, but know that there's a way to get the real part and the imaginary part. So if I just look at it, what are we gonna get? Well, I'm gonna get here, I'm gonna get the exponent of negative 4.111, sorry, negative 0.4111. Negative 0.4111 times t. And then I'm going to multiply everything by the real part of the eigenvector associated with this eigenvalue, which is this one right here. So I'm going to multiply everything by the vector minus 0.6667, and it's actually 3 parts, so it's negative 0.333 semicolon, this is the second entry, third entry is 1, that's my vector, multiplied by the cosine of the imaginary part of the vector, which is 0. Sorry, not the imaginary part of the vector, the imaginary part of the value, which is 0.1449 times t. And then I'm going to subtract here. I'm going to subtract the other eigenvector part, which is the imaginary part, which is 0.8692, semicolon, negative 0.8692, semicolon, 0. And that's going to be multiplied by the sine of this. Copy, paste in there. So that's going to be a second solution, right? And now a third one is going to have the exponent of, now we need to go over here. And the value is going to have to be this over here. So the exponent of this value, 0.411. And it happens to be actually the same. So 0.4 because they're complex conjugates. So it's this one, then I'm going to multiply it by, I'm just going to copy this. I remember I showed you this in a different video. I just can't find it right now. And then from this, what I can do is I can just say, well, now I want the imaginary part here. I want the imaginary part here. I want the real part here. And I want this to be a plus. And now, forming the general solution, what am I going to get? I'm going to get x, well, x of t is equal to c1 times x1 plus c2 times x2 plus c3 times x3. And now what I want to do is is just leave it like this. Okay, so Control Enter. Control Enter. Unrecognized function and variable because we haven't defined these. So C1, C2, C3. Pressing Control Enter here. And here we get what our solution is